In this example, we're going to try to show whether a series is absolutely convergent, conditionally convergent, or just flat out divergent. So a series we're going to look at is a series -1 to the n times 5n all over n factorial. Remember, with any of these types of absolute, conditional convergence, divergence problems, the first thing we really ask ourselves is, well, what test are we going to use here? So we like looking for if we can use ratio test first. And the first thing we do for looking for ratio test is, well, does the series function have any of the three types of functions that really indicate, hey, ratio test is useful here? And in this case, we actually see our series function has a few of them. For example, this 5 to the n. Basically, this 5 to the n is a number raised to the power of n type term. So it's one of the things that says, you know what, we could use ratio test. However, we also see we have a factorial here. So this factorial would be enough alone to say, you know what, we should try ratio test on this problem. Actually, the only thing that doesn't say ratio test is this -1 to the n. This doesn't really tell us that ratio test is useful because we need any other number raised to the nth power to use ratio test. But this 5 to the n or the n factorial is enough for us to say, you know what, let's give ratio test a go. And the way in which we use ratio test is basically we're going to take a limit now. We're going to take our series function of the nth, or the nth series function. So an here is just, well, that's the original function that we're given. -1 to the n times 5n all over n factorial. And we look at what the next general term is, the n plus first. So anywhere there's an n, we basically replace that with an n plus 1. So we get -1 to the n plus 1, a 5 to the n plus 1, and we also get a divide by n plus 1, that quantity factorial. So we're going to take those two things, take a ratio of them, and take a limit as n goes to infinity in absolute values. And depending on what that limit looks like, will tell us whether or not ratio test guarantees this series is absolutely convergent or divergent. I just also want to mention that ratio test cannot be used to show a series is conditionally convergent. And that's based on the fact alone that those functions that indicate we're using ratio test, numbers raised to the power of n factorials, n to the n type stuff, those functions are growing so fast that the series really only has two options. It's either going to be absolutely convergent or divergent at that point. All right, well, let's go and apply ratio test. So we take the limit as n goes to infinity of the absolute value of our series n plus 1 term and the nth term. So let's just plug in all of that stuff now. So limit as n goes to infinity of the n plus first term. So we have -1 to the n plus 1 times a 5n, or 5 to the n plus 1, all over n plus 1 factorial. And we divide that by the an, or the nth term of the series, which is a -1 to the n times a 5 to the n all over n factorial. And now, since we're taking a ratio of lots of fractions and things like that, I always like spending a little bit of time to rewrite this just so I don't make any algebraic snafus or algebraic goofs. So what I mean by that is, basically I'll take any fraction and just reciprocate it and multiply it on. So the first thing you could see is, well, we have a -1 to the n plus 1, a -1 to the n. Those terms are kind of just hanging out by themselves, so I'll just write them first. So you have a -1 to the n plus 1 all over a -1 to the n. But next, I really do want to just take the denominator of the original fraction, reciprocate that, and multiply it on. So I'll still have the 5 to the n plus 1 all over n plus 1 factorial, but now I'll reciprocate that original denominator and multiply it. So we get an n factorial all over 5 to the n. And now that we have everything we're multiplying by, I'm just going to start grouping similar terms together, almost like what we did for the -1 term. So you have a -1 to the n plus 1, a -1 to the n, multiply this by 5 to the n plus 1, all over a 5 to the n, and then finally an n factorial all over an n plus 1 factorial. And the reason I like doing this is so I can more easily cancel stuff out and do the algebra a little bit more streamlined. So for example, this first term, we see each of these things have a minus 1 to the n, so we're really just left with a minus 1. Next, we can take a look at this 5 to the n plus 1. We could rewrite this as, well, 5 to the n times a 5 to the first power, because when we have the same base and we're raising them to different powers and multiplying, we just add their powers together. So we can see we can cancel out a 5 to the n and a 5 to the n. Next, what we have is this n factorial all over n plus 1 factorial. And while using properties of factorials, we could write this n plus 1 quantity factorial as a n plus 1 times n factorial. And the reason for doing that is, well, we can then cancel out the n factorials. So we're just left with a n plus 1 in that denominator. So let's just rewrite everything that we have. We have the limit as n goes to infinity of the absolute value. We have this minus 1. We next have times 5. And then finally, from this last term, we just have that n plus 1 now in the denominator. And now you might notice, well, we have this minus 1 here, and we're taking the absolute values of everything. So actually, we can get rid of that minus 1, or really the absolute values of minus 1, that just becomes a positive 1. So rewriting this, what we're really taking the limit of now, the limit as n goes to infinity of the absolute value of 5 all over n plus 1. And now let's just take a pause for a second, because what we want to know is, what's the outcome of this limit? And depending on this outcome will tell us whether or not this series is absolutely convergent or divergent, or if we've applied ratio test when we shouldn't have, so-called getting an inconclusive result. So if this limit is less than 1, that tells us that the series is absolutely convergent. If this limit is greater than 1, this tells us that the series is divergent. If this limit equaled 1, well, it's inconclusive, basically saying you probably applied ratio tests when we shouldn't have, or something like that. Or we can use a different test to determine whether this is absolutely convergent or conditionally convergent. But ratio test isn't going to help us out here. So looking at this limit, as n goes to infinity, what we see is, well, this numerator, that's just a finite number, so that's not growing at all. But this denominator, as n goes to infinity, this denominator is growing off towards infinity. So this looks like a finite number sitting on top of a number that's blowing up larger and larger. So this limit is equal to 0. And now we'll use what the ratio test conditions. We see, well, 0, that is indeed less than 1. So by ratio test, this series is absolutely convergent. And remember, what absolute convergence buys us is the ability that if we take our original series, really only look at each term being positive and adding that together, we could sprinkle in as many minus signs as we want into that series, and that series would be guaranteed to converge. So absolute convergence really tells us a lot about, well, the series with only positive terms converges. Then we can put in as many minus signs, and that resulting series will still converge.